All right, so in this section, we're going to look at trees. A tree is defined to be a graph that is connected and has no cycles. The rest of these definitions are pretty intuitive. A forest is a graph whose components are trees. Vertices of degree 1, so a vertex sort of at the ends, those are leaves, and all the other vertices are called internal vertices. And then directed tree is loop-free directed graph whose underlying graph is a tree. Such that if there is a path from A to B, then it is unique. And if it has no loops, certainly if AB is a directed edge of a directed tree, then BA cannot be a directed edge of the graph. So I'm just going to make a couple of observations. One, that a tree with at least one edge has at least two vertices with degree 1. And so we're going to kind of figure out why this is. And we're going to start, let's just let T be a tree. So it is connected with no cycles. And suppose there is a path that is a maximal path. And by maximal path, we mean a path that cannot be extended. And let's suppose further, this maximal path, say, starts at vertex A and ends at vertex B. So what a path like that might look like. Here's vertex A. Here's a tree. It's connected. It's got no loops. I'm just sort of making this up, but maybe there's vertex A on the left and vertex B here. And this path that we have now, this is maximal, meaning it can't be extended, meaning it can't be extended on the A side, so there's no edge leading out of A. It can't be extended on the B side, there's no edge leading out of B. If that is a maximal path, then the degree of A has to be 1, and the degree of B also has to be 1. If the degrees of A or B were anything other than 1, then the path wouldn't be maximal because we'd have a way to continue the path. And then a maximal path is not necessarily the longest path. There's a difference between the word maximal and maximum. So maximal just means it cannot be extended beyond what its limits are. So I'm going to draw a graph here. I'll call this V0. Here's V1 and V2. So we've got V3, V4, V5, V6, and then V7 and V8. So I'm going to draw you a maximal path that is not maximum length. So here's a path, V3 to V1 to V5. That is a maximal path. Because it can't be extended on either side. But it's not a path of maximum length. Certainly I could draw a longer path from V4 to V1 to V0 to V2 to V6. That is a longer path. It's not maximal, but here's another longer path that's still maximal if I end at V7. So V4, V1, V0, V2, V6, V7 is longer. And I think that might be a path of maximum length in that graph. So let's establish some results here. say we've got a tree, so a connected graph with no cycles. For any two vertices, A and B of a tree, then there is a unique, simple path from A to B. So a simple path, remember, is a path where no edge is repeated. So, and we're saying that there's a unique simple path. There's only one way to get from A to B. And we're going to prove this by contrapositive. So we will show that if there is no unique simple path, from A to B, then T is not a tree. So let's let A and B be two vertices of T. And suppose there's no unique path from A to B. So if there's no unique simple path from A to B, then one of the following is going to be true. Either there's simply no path at all, in which case T is not connected and can't be a tree. Or the other option is if there's no unique simple path, that means that there exist two distinct paths, at least two, but let's just say there are two. Are two distinct paths. From A to B. Let's say the first path starts at A, then B1, B2, B3, all the way up to Vn, which is equal to B. That's our B vertex. And I'll just call this path 1. And path number 2 again begins at A, and then it goes to V1 prime, V2 prime, V3 prime, all the way up to, I don't know, Vm, which is our B vertex. Vm prime, I should say. So these both start and end at the same vertex. That means that there must be a first vertex where they disagree. Like maybe V1 is the same as V1 prime and V2 is the same as V2 prime, but there's going to be a point, if there are distinct paths, where the paths have to part ways. Let's say, there must be a first vertex where the paths diverge. Say Vi not equal to Vi prime. So here's what this looks like so far if I were to kind of draw. We're starting at vertex A, and then this path goes to V1, V2, V3, and maybe for a while these paths are the same, right? And it keeps going, but then there's a first vertex where they're different. So where there's this sort of branching. So there's our VI and VI prime. So the last vertex where they agree is VI minus 1 is the same as VI minus 1 prime. All right, so that's where the paths first diverge. But look, they end at the same vertex, right? They both end at B. So similarly, there has to be a vertex where the paths converge again. Now that the next time they converge could be at the vertex B, but it could be earlier. We just know that it happens. Let's say that happens at VK in the first path, and that is the same as the vertex, say, VJ prime in the other path. I'm using different subscripts because the paths could be different lengths. In the beginning, you know, the paths are the same length as long as they're agreeing, right? Those subscripts are the same as you go along. And then they diverge. One path might do one thing, another path might do another thing, you know, have different lengths. But then eventually they converge again. And that's at this vertex here, which is VK in the first path, and we called it, say, VJ prime in the other path. And then there's some other vertices maybe before we get to the ending path, the ending vertex, which is vertex B. So maybe you see it already. It's especially salient if you look at the sketch there, at the diagram, at the graph. But if we have two different ways to get from A to B, there's a vertex in which they first disagree, right? That happens here, right? That's where they converge. And then there's a vertex where they agree again, so they converge again. So the paths diverge and then they converge, and that means that what we have right here, what we know must exist in the middle of this tree, is a cycle. So let's write it down. We can write it down, so we're starting at VI minus 1, right at the top of that cycle. And then to VI. And then, you know, there's a bunch of stuff that happens, and then we get to VK, which is the same as VJ prime. Those are the same vertex. And then you keep going now back up along the path in the counterclockwise direction, and we get to VI prime and then VI minus 1, right? So starting and ending at the same vertex. There's our cycle. So T is not a tree. That means that by contrapositive, if T is a tree, then there's a unique simple path. Then there's a unique simple path connecting any two vertices. Okay. Let's take a look at the next theorem, which is just the converse of the other theorem. Now we're going to say, suppose we have a graph G, any old graph, and then if for any two vertices there is a unique simple path from A to B, then G is a tree. So We're going to prove this one also by contrapositive. And the contrapositive statement is, if G is not a tree, then there is no unique simple path. For two vertices, meaning that we could find two vertices for which there is no unique simple path. So, okay, let's suppose G is not a tree. If G is not a tree, remember a tree is a graph that is connected and has no cycles. So if G is not a tree, then one of the following must be true. Either it's not connected, or it has a cycle. So we'll take these one at a time. If G is not connected, then there exists two vertices for which there is no path between them, and certainly then no unique path. We'll call these vertices A and B. So there's the first case. If it's the second case, if it has a cycle, then we're going to basically be able to find two distinct paths from between a couple of vertices. So if G has a cycle, let's write it down. Right, let's say it starts at B0, goes to B1, to B2, to VK minus 1, to VK, and then ending at V0. So if there's a cycle, say that we can write out like that, then there are two distinct paths from, say, V1 to V2. One path is just going from V1 straight to V2, right, in that direction. The other path is if I start at V1, but then I go backwards. So this would look like V1, V0, VK, VK minus 1, back down to V2. So that means that there's no unique simple path from V1 to V2. And by contrapositive, we know that if we have a graph where between any two vertices there's a unique simple path from one vertex to the other, then G must be a tree. So this essence of having a unique simple path between two vertices is synonymous, is really another way to define what a tree is. Okay. So now we're going to do a little bit of visualization and kind of redrawing some graphs. These happen to be trees. They're connected, right? This graph is a tree. It's connected. There are definitely no cycles. Now imagine that these vertices are hinges. So if I could, for example, like imagine picking it up by one vertex, then the rest of the tree would kind of hang down below it. When we choose a vertex at which to like kind of hold up that tree, we say that we're picking a root. So if we were to kind of distinguish V3 as being a root and redraw it, then V3 is at the top here. And down below, let's see, on one side I'm going to have V2, and hanging below that is V0 and V1. And then on the other side I've got V4, from V4 I've got V8, and then V5, and then hanging down below V5 is V7 and V6. So here we've kind of distinguished V3 as being a root, and we're going to define that. That'll show up in the definition on the next page, I think. And we've imposed a sense of like hierarchy on the tree when we do that. We can do this one more time. Let's say we want to hold the tree by the vertex V4. So if we pick V4 to be our root, I'm going to zoom out so that we can hopefully see this as we draw it. So we're starting, V4 is at the top, and then hanging down from V4 I've got three vertices. I've got V3, I've got V8, and I've got V5. Off of V5 I've got V7 and V6. And off of V3 I've got V2, and then V0 and V1. All right, so when we do this, we call it a rooted tree because we have distinguished a root. If we have a rooted tree, we can easily change it to a directed rooted tree where we just direct, add direction to each of the edges. Once we have a rooted tree, as I mentioned before, we kind of have a bit of a hierarchy. So the level of a vertex is the length of the unique path from the root to that vertex. So if I look at this graph where V4 is the root, then V4 is level 0 because that is the root. Here are the level 1 vertices, and then here are the level 2 vertices, and then we got some level 3 vertices. The highest level is considered the height of the tree, so this tree has a height equal to 3. So a directed rooted tree, we just add direction. We make all the edges directed edges, and they're directed downward from the root. In this case, so in this example, we just have a rooted tree with the root at V0. The derived rooted directed tree rather is the one where we just add all these directions to the edges as we've already done. What is the level of V4? Well, V4 is level 2. Right, all of these vertices here are level 2, and that's the length of that's the the highest level of a tree. That's the length of the longest path from any vertex to the root. And so the height of the tree has height 2. And some more terms regarding rooted trees. If there's direction to these, right, so we have even more hierarchy, right, not even just establishing a root, but that there's a direction to these edges. We use a lot of these terms that kind of are synonymous with like thinking about a family tree. We say that U is the parent of V if there's a directed edge from U to V. So for example, V2 is the parent of V6. And V5 and V6 are considered siblings because they share a parent. If there's a path, not necessarily just a single edge, from one vertex to the other, we say that the top vertex is the ancestor. So for example, like V4 is a descendant of V0, even though it's not just a single edge, right? It's a path of length 2. We say that V4 is a descendant of V0. We say that V0 is an ancestor of V4. If the largest out degree of a vertex is degree M, then the tree is called an M-ary tree, so that's sort of like a weird language to use. But if M is 2, it's called a binary tree. If M is 3, it's called a ternary tree. Once you get to bigger numbers, that's when we just say, oh, that's a 7-ary tree. Although I'll say that trees with the degrees of 7 or higher are probably not as common as the lower degree trees. In every binary tree, each child is designated as either left child or a right child, but not both. So in this tree, let's identify a parent and child. So for example, V5 and V2, right? V5 is the child of V2. Equivalently, V2 is a parent of V5. V5 and V6 are siblings. I'm kind of picking on that side of the graph there, but you get the idea. An ancestor and a descendant. So maybe look at V8 to V1. That's path 2. I could make it path 3 and go all the way up to V0. But we know that V1 is an ancestor of V8. V8 is a descendant of V1. A right child and a left child. Let's see. So maybe look at V1 and V2. So V1 is a left child, V2 is a right child. Okay, let's prove another result. This one won't take too long. If T is a tree, then it has E edges and V vertices, then V is equal to E plus 1. So in a tree, the number of vertices is always one more than the number of edges, is what they're saying here. So to prove this, what we're going to do first is pick a root of the tree. We'll note that this does not change the number of vertices or edges. Now we have this rooted tree. Let's consider the derived rooted directed tree. Right, so all directions kind of emanate downward from the root. Call this T prime. So in T prime, each edge has one terminal vertex, and each vertex is the terminal vertex of one edge. So let's see, each edge has one terminal vertex. And that's true always in any directed graph. Each edge has just one terminal vertex. But each vertex is the terminal vertex of one edge, because there are no cycles in this tree. And there's only one exception to this. And that is the root, which is not a terminal vertex for any edge. So now, not including the root, if we just don't consider that vertex for a moment. If we don't include the root, then that means that the number of vertices is equal to the number of edges. Now if we throw in the root, then the number of vertices is the number of edges plus 1, as desired. All right, so this next result is going to kind of build on what we know about the relationship between the number of vertices and edges of a tree if we have a graph that's connected with E edges and V vertices, and we know that this equation holds, that V is equal to E plus 1, then G must be a tree. So we're going to suppose G is that G is connected and that V is equal to E plus 1. We will show that G is a tree. Well, let's suppose for contradiction that G is not a tree. That means that since we know by supposition that G is connected, if G is not a tree, that means it has a cycle. So let's grab an edge in that cycle. If, let's say, VI, Vj is an edge in the cycle, that means that there are two paths from Vi to Vj. There are two paths from between any two vertices in a cycle, so certainly from Vi to Vj. If there are two paths from VI to VJ, that means that we could remove that edge, right? This edge VI, VJ, we can remove that edge, and there will still be a path from VI to VJ, and the graph would still be connected. So let's remove this edge. So we've removed an edge, we still have a connected graph. If there's another cycle, we'll just repeat this process. Repeat this process until we have a graph. I'll call it G prime. That is still connected but has no cycles. So in this process, we didn't remove any vertices. So G prime still has V vertices. But we did remove some edges, so there's a different number of edges. We'll say it has E prime edges. G prime is a tree because there's no cycles and we knew it was still connected. And by the last theorem, which was theorem 4.6, we know that V is equal to E prime plus 1, right? The number of vertices in a tree is one more than the number of edges. So say in this whole process that we went through where we said, oh, here's a cycle, let's remove an edge. If there's another cycle, we can remove another edge, right? And we go through this whole process where we remove some number of edges until we get this tree that's still connected but has no more cycles. So suppose in this process we removed n edges. Then the number of edges we started with in our original graph G is going to be equal to E prime plus n. Right? We removed the n edges to get the E prime edges in our tree G prime. But this is really important here. I'm going to go back to part of our supposition. We suppose that G is connected and that V is equal to E plus 1. So this is the part I want to draw your attention to here. This is a part of our supposition. So if V is equal to E plus 1, as we have here, and V is equal to E naught plus 1, this means that E has to equal E naught. Or not E naught, but E prime rather. And so n is equal to 0. This means we didn't remove any edges to get G prime. That means that G had no cycles to begin with. And G is a tree, as desired. Okay. So we know that a tree is connected with no cycles. There's sort of like an efficiency to that. There's no extra edges put in, right, in order to keep our graph connected, in sort of one way to think about it. Any graph that's connected has a spanning tree. And what a spanning tree for a graph, let's say you have a graph G, a spanning tree is a subgraph that is a tree and includes every vertex in G, but probably not every edge unless G is already a tree, right? So as it turns out, every connected graph has a subgraph which is a spanning tree. We're not going to prove this theorem, but to find a spanning tree, you could simply follow the procedure that we described in the last theorem. So I mean, and really going through that theorem is kind of like how you would build a proof of this theorem, or going through that process is sort of how you build a proof of this theorem. But to find a spanning tree, just follow the procedure in theorem 4.7. That graph G prime that we talked about in that theorem at the end of that procedure is the spanning tree. Is a spanning tree. A graph can have more than one. So a quick example. Here's a graph. I'm going to draw a graph here with 6 vertices. So it's connected. Every connected graph has a spanning tree, and we're just going to go through the procedure here. This is not a tree already. It's definitely got cycles. So in one iteration, I'm going to identify a cycle. Let's say the cycle, this sort of box on the right side, the V1, V2, V5, V4. Here's a cycle. I'm going to identify an edge in that cycle and get rid of it. I'm not going to get rid of any vertices. So I'm getting rid of one edge. Oops, got rid of that edge. So that's what we're left with. Now I've got another cycle still. So I'm going to pick an edge in that cycle and get rid of it. Doesn't really matter which edge I pick. So let's say I pick this one from V3 to V4. Then we're going to have that edge, and this edge, and this edge, and that edge, and that edge. Now there are no more cycles, so this is a spanning tree. And as long as your graph is connected, it'll have a spanning tree.